So in this problem, we are asked to turn this heck of a molecule. Notice how we have a diester here, and we have, or an acetal, I should say, correct terminology, and we have an ester. So if we reacted with acid, aqueous acid, and we heat that thing up, we're going to get a molecule with the molecular formula of C10H10O. So, can we devise a scheme for which one we're going to create? First, we need to actually predict the product. But to do that, we have to write out the mechanism. So let's go ahead and do that. I'm going to redraw my starting material. So what's one thing that we can do? There's going to be I'm going to just tell you now. There's multiple things that's going to happen. Let's identify what those things are. I'm going to notice that I have a group here. What happens when you react an ester with water and under acidic conditions? Well, you know it's going to form a carboxylic acid. So that's going to happen. We know that. So we'll write that mechanism there when we get to it. Notice we also have an acetal. What happens to acetals when you introduce water to them? Well, they're going to hydrolyze back into a ketone, right? Remember that equilibrium that you've probably seen, right? If we have a ketone and an acetal, so I'll write OH, OH, right? To go this way, to favor that reaction, we need to just use, and let's just say we use, instead of a hydrate, let's form acetals with ethyl groups, ethoxides attached to it. We would want to use Na, O, and then the ethyl, and then, you'd use the corresponding alcohol, ethanol, and you'd use acid, H2SO4. To go in the reverse, we just use H2SO4, and we're also going to use water, right? Because what's going to happen is it's going to hydrolyze that. It's more favored to go that way. So when you do these reactions and you want to make the acetal, you need to evacuate water from your vessel. Okay? So that's exactly another thing that's going to happen. So we'll go ahead and draw that. For those who don't remember the mechanisms, I'll write them out, because why not? I won't make you go back and look. Sorry for the people that may know the mechanism. Maybe draw it out yourself, get a little bit of review in there. So the first thing that happens is we will, let's do the ester hydrolysis first. So knowing that carbonyl is kind of tight, it's going to be like, I ain't moving, so we need to do what's called an activation of the carbonyl. That's going to involve, and I'm just going to write, this squiggle is representing the whole rest of this molecule. But just so I don't have to draw so much, I'll draw it as squiggles. So we have the OH there, which activates the carbonyl, which allows an equivalent of water to come in and attack, kick up electrons. And we're going to get this here. Now, I'm going to just skip a step. Hopefully you see it. Notice this oxygen has a positive charge, and it can be stabilized by deprotonation from, say, water. So that's exactly what's going to happen. I won't bother drawing it out. So we have a hydrate here. Now what's going to happen is we're going to protonate this ester group. Let me see if you can see what I'm drawing. Nope, you're going to get cut off, so let me come back around. So what happens here is we're going to protonate this by H3O. Could you imagine if I had to draw the molecule every single time for this? You see why I make the shortcut? Anyways, so this is now protonated, which allows one of our alcohols to come in and kick him off. He's like, nope, bye-bye, you're gone, you're done, off the schedule. Yeah, I've had that text quite a few times. You're off the schedule, Corbin. Man, that's awful to receive. Sorry, I'm like trauma dumping you guys for organic chemistry. Isn't it kind of fun? I love organic chemistry, it's great. A lot of fun things. Okay, And finally, we're going to take our water and we deprotonate. Quite simple. So we're left with this. So we did the carboxylic acid hydrolysis. Now we need to do the acetal hydrolysis. That's pretty simple. Using acid, we're going to protonate one of the sides. So we'll say H2 plus charge here. We're going to pick up a hydrogen and reform water. Oh, hello, Jack. I'm in the middle of a lecture here.
Sorry.
You want to stand? You want to say hello to everyone? I'll be done quick, but say hello, everyone. Jack's making another appearance. Do you know what this reaction is called, Jack?
No.
I don't either. It's a lot. So we're going to protonate our protecting group acetal here. So it has the hydrogen here, and what that allows is for water to come in. And basically, he's just going to say, nope, you're gone. And I'm going to draw more of the squiggles because this is going to get complicated. So what happens here is we have our water attached. It kind of gets keyed off. So what happens is we have the positive charge on the water, and we have our ester, which comes in like this. 1, 2, 3, OH. We're going to just deprotonate. I'm going to skip this step here, but water just comes in, deprotonates, and we have an OH here. And again, to keep things simple, you've probably learned this reaction already. I'm just going to draw multiple arrows to show this happens again. On this side, water comes in, kicks it off, gets deprotonated. So 2 steps, actually. So we're going to get hydrolyzed acetal, or hydrolyzed acetal product, I should say. And we get this here. But we're not done yet. Notice that's a hydrate, and we know under conditions where there's water, this will reform the carbonyl, because hydrates are not formed in great quantities at equilibrium for these bigger molecules. So I'm not going to draw that mechanism because that gets annoying, but basically this gets protonated. The OH will form a carbonyl, kick out the water, and this will be deprotonated off. So we get this here. And we're left with this. So we're almost at the end. There's a little bit left. And that has to do with this carboxylic acid. When you heat a carboxylic acid, if you recall what happens with that, is that we're going to stress the molecule. It's going to cleave a hydrogen here. And this is called beta decarboxylation because it's alpha beta. It's in the beta position. So this gets a negative charge. It folds in electrons and kicks a group here to form an enolate. So let's draw that in. Remember, this is still under acidic conditions. So this is not very likely to happen where we deprotonate. That's why we have to heat it to really drive that equilibrium. But we do lose CO2, and once that happens, it bubbles out of solution, and it's irreversible. So we have our negative charge here, and remember, if this is an acid, we just take a proton in solution, and we deprotonate. So our final product here, and we'll check our work just to make sure that we are correct, is this here. Oh, that was a lot of steps, but so to summarize, under acidic conditions and heated, the ester is going to get hydrolyzed into carboxylic acid. Then we'll undergo beta decarboxylation from the heat. It's going to stress the molecule to leave as CO2, and that group just completely leaves off the molecule. When we use acid and heat on this protecting group, this cyclic acetal is what we call it, what happens is it's going to be, where do we start this? We form a hydrate, right? So the OH, and then that gets eliminated into a carbonyl, and that carbonyl just stays. It doesn't undergo any reaction under the heat and acidic conditions. Hope you guys enjoyed. If you did, please drop a like, comment if you have any questions, and subscribe, please. Have a wonderful day.